Good afternoon, everyone. I hope you all enjoyed lunch and you can hear me loud and clear. Very welcome in this almost final session on the CAMS R&D supporting projects. It's my pleasure to be here at the General Assembly, and I hope that the event so far has been very interesting and productive for all of you. So in this session, we will give you some interesting insights into our 6 EU-funded R&D projects and how they have been or how they still are in fact contributing to the evolution of various aspects of CAMS. So I'll give a brief introduction from my side, from HDEA, and then I'll give the floor to the project representatives from each of the projects to give you some more details on each of the projects, the objectives, their main achievements as well. As in the previous sessions, there's room for Q&A, hopefully a bit after each of the presentations. With that being said, I'm checking if my presentation is set. There we go. My name is Lucas Lano. I'm a project advisor at HDEA. I'm pretty sure that not all of you are familiar with HDEA, so very briefly, HDEA is short for the European Health and Digital Executive Agency. We manage projects on behalf of the European Commission in, as our name indicates, health and digital, but also other areas, including food, industry. And the reason why I'm here today is because we also have an important portfolio of EU space research projects as well. Very briefly, we're an executive agency. That means that we work in close collaboration with what we call our parent DG. In the case of our space research unit, these are our excellent colleagues at DG DEFIS, some of who you, of course, have already seen here in the past days as well. And we like to say that as an agency, our policy colleagues are making the policies and we are turning the policies into actions in the field, meaning that we organize the call for proposals and make sure that the best research projects are selected, and we monitor the successful implementation of our projects, and we try to close the loop by monitoring what is coming out of the projects and communicating that back to the colleagues at DG DEFIS. As I mentioned, as an agency, we're working in many different areas. What's only important for you to know here today is that our space research projects are being funded under Horizon Europe, which most of you will know is the currently running framework program for research and innovation. At our unit, we're managing several parts of the space research portfolio. What I want to highlight here today is our family of projects that are supporting the evolution of the Copernicus services. Of course, not only CAMS, also the other thematic Copernicus services as well. As I mentioned, funded under Horizon Europe, but also building on a strong legacy of projects under Horizon 2020, which was the predecessor program of Horizon Europe. I will not bore you with all of the details on the exact organization of Horizon Europe, just for you to know that our space research calls are located in the 4th cluster, which is the cluster on digital industry and space in Pillar 2 of the Horizon Europe program, where under our space calls you will find also our topics that are supporting the evolution of the Copernicus services. And what is the goal of these projects? Well, overall, you could say that with this, the European Commission is supporting what is referred to as Tier 3 research and innovation projects. That means that these are not short-term operational upgrades of services such as CAMS, but that we're really supporting, you could say, more riskier R&D projects that aim for medium to long-term upgrades of the different services, really focusing on a period of several years indeed. As I mentioned, primarily funded under Horizon Europe under this cluster 4, there are also other calls and topics that are contributing to the evolution of the services, of course, and there are complementary efforts under the national research programs as well. The main goal is, you could say, to enable the Copernicus services as a user-driven program to also make sure that they are evolving in line with new user requirements, with new policy challenges, and that they're also able to leverage really on the latest available state-of-the-art scientific and technological developments. And at HDEA, we are very proud of our portfolio of Copernicus service evolution projects. As I mentioned, we are supporting CAMS. You see on the top 2 rows 6 projects that we'll be presenting in this session. I'll give you a bit more info in the next slide. But as I mentioned, we have projects also supporting the climate change, marine, land, security, and emergency services as well. And we have our portfolio of cross-cutting projects, so projects that are supporting multiple of these services. Of course, where possible, these projects are always looking for cross-service synergies as well. You see in the top row that these are our last 3 waves of projects, you could say. So we had our last calls under Horizon 2020 with many projects. We had our first calls under Horizon Europe. And then last year we added 5 additional projects under the 23 space call as well. And the work doesn't stop, so the pipeline with projects continues, of course. We're, as we speak, finalizing the evaluations of our 24 space call, and where we will be adding 4 additional Copernicus evolution projects, 2 for Copernicus for land and water, and 2 in the domain related to security. But let's zoom into the 6 projects that will be presented. I'll leave the details, of course, up to the 6 presenters that will be up next. But to give you a brief overview, you could say that there are 2 main lines of activities. Top 3 projects are projects that you could say are more working in the area of atmospheric pollutants. Bottom 3 projects are the ones that are supporting the preparation of the CO2 MVS, which has been explained in detail this morning, I think, by Richard as well. Taking a look at the top 3 projects, we had the Horizon 2020 Seeds project. That project ended in the end of 23. That was coordinated by Nilu and was working on an add-on service for air pollutant emission and deposition products. There's the ongoing Cameo project. I think we've already heard several references in the previous presentations as well. That project, coordinated by ECMWF, is focused on the one hand on improved data simulation methods, as well as working on the development of improved uncertainty information for selected atmospheric products. Our most recent addition is the Camera project, coordinated by Hygeos, which is on aerosol, working on improved global and regional aerosol modeling capacities, as well with a focus there on secondary aerosols and precursor gases. Moving to the bottom line of projects, I don't think I have to repeat the importance of the CO2 MVS capacity in view of the upcoming Sentinels, not in the least the CO2M constellation, of course, as well as their importance to contributing to the related international initiatives, frameworks, global stocktake process, the WMO, Global Greenhouse Gas Watch, to name a few. And as mentioned by Richard, this project didn't start from scratch. We're building on the extensive efforts from successful predecessor projects, such as CAMS Verify, as mentioned by Richard. COCO2, I think most of you will know that project by now. Very big project, ended in the end of last year. Really important in contributing to the preparations of the CO2 MVS prototype systems. There's the Corso project, that is focusing on better use of co-emitted species and auxiliary observations to improve the separation between anthropogenic and biogenic CO2 emissions. And the most recent addition there is the project Catherine, which is working on evaluating and improving the numerical schemes for the transport of atmospheric tracers. All 3 of these projects are coordinated by ECMWF. Now, that being said, of course, I only included here the coordinators on the slides, but behind each of these projects are often very substantial consortia, international complementary consortia of partners that, of course, make this project a reality. To give you an idea, these 6 projects combined represent 94 project partners, so we're really talking about vast international coordinated efforts here. To conclude, I think we can say that overall these projects are really fundamentally important for the long-term evolution of CAMS, and that they hopefully also provide substantial potential for future service improvements as well. But I'm sure the 6 speakers will be able to convince you of that in the next presentations. I want to end my introduction with a bit of a forward-looking angle. So as some of you might have seen, there was last month publication of the EO Strategic Research and Innovation Agenda. This is an important document because it serves as the main framework, as the main reference document for the development of the next calls under the upcoming Horizon Europe Work Program 25-27, and even for the initial preparations looking beyond Horizon Europe, so looking to its successor, the next framework program as well. I invite all of you to download the report. You can find there for each of the services the short-term and long-term R&D priorities. On that note, yes, our communication colleagues will be happy if you follow us on Twitter and LinkedIn to stay up to date on our upcoming calls and our ongoing projects. And without further ado, I will then pass the floor to our first speaker. And if my notes are right, that should be Luca Cantarello from ECMWF, who will be telling us about the COCO 2 project. Thank you very much.
Okay, can you hear me? Yes, I think you can. So, good afternoon. Hopefully my presentation will come up. I'm Luca. I work at ECMWF, and I was tasked with the challenging task of giving, in 12 minutes, a summary of the COCO 2 project, which lasted 3 years, and it ended last year in December, and I was part of this project. So hopefully, oh, yeah, it's coming. Okay, so as you can see from this slide, there were many people involved in this project across 14 European countries, European and non-European countries. And so if there are people that were in COCO 2 in this room, please bear with me if your results are not in the presentation. It was very challenging to put together a comprehensive summary of all the activities that took place. So my presentation will not go too much in details. It will be an overview of what has happened in the project and what were the main activities that were carried on and that carried out. So I think it would be nice. It was nice to look at this slide again, which you have probably seen already a few times in these last 2 days. The reason is because this is supposed to be the structure of the CO2 MVS, but somehow this is also resembling quite a lot the structure of the COCO 2 project, as you will see later in the work packages scheme. And basically the idea here is that we start from some prior information we have, and then we have some observations of the Earth, and we put them together using all the tools that we know from Earth modeling, data simulation, emission inversions, and we come up with an output that then needs to be shared with some users in order to support the implementation of the Paris Agreement. Previous slide. Yes. So you also have seen these slides a few times already, I think. And so COCO 2, COCO 2 was here. We started in 2021. But again, it was not the start of this long-term plan that we have to get to the CO2 MVS. It was just one of the steps. But it was very important because the idea was basically building a prototype for what will be one day the CO2 MVS. And of course, COCO 2 has been followed by other projects which just build up on it and on its results. And so this is the project structure. You can see here we found again the points that we had in 2 slides, 2 slides ago. Which are basically there is a core part of the project called integration, which includes all the modeling and data simulation and inversions parts, which included packages 3, 4, 5, and 6. But then we also have as inputs to this some work done on the observations and some prior information. And then, of course, we have an output, and again, output which links to some kind of interaction with the users. So what I will do now is I will go through each work with one slide for each work package and try to give you an idea of what were the main activities that were carried out. So work package 2 had the task of basically coming up with some prior emission data sets which then were then used in other work packages. And here I've just pasted some, like a summary of some of the things that were done. So some people, for example, produced some regional prior emission data sets. Some people produced global prior emission data sets. Some people focused on the temporal profiles of these emission data sets. And some others came up with point sources estimates. And then other people as well try to estimate the uncertainties related to these emissions. And this was very useful work because then it could be used by other people to do the modeling and all the other activities that were part of the project. Work package 3 was the part of the integration, the core modeling part of this project. And so and included basically all the global modeling and the data simulation developments. So for example, at ECMWF, we developed this NATO RANS simulation that you might have seen in other presentations, which are very nice, and they just show like the evolution in time of tracers like CO2 and methane. But then there were also other activities all around Europe related to just producing, running some inversion modeling at a global scale, testing all sorts of setups and configurations. And some people also try to estimate the land use emissions using satellite observations through emission inversion. Work package 4 was also on the modeling and data simulation, but it went from the global scale to the very local, regional, if not very, very local scales, because we had here, for example, plume inversions activities, even overlapping with AI, machine learning modeling, or modeling based on machine learning. And then there was a lot of work done on national level, national scale level of inversions done by many institutes. I think there were 11 or maybe 10 different models run to come up with inversions at the national scale. And then, since I've talked about global scales and local scales, then there was another work package which had the task of putting this thing together, or maybe creating a channel for them to communicate from one to the other. So, for example, at ECMWF, we spent a lot of time trying to develop an EDA, so an ensemble, extending our ensemble of data simulation to greenhouse gases to, in a way that we could actually provide other partners in the project to run regional scale inversions with some boundary conditions that could be attained by the global system. And so part of this package was both the activity done to all the activity done to transfer the information from the global to the local scale. And here you see some results of the inversion run at the region using regional models. And then related to this, there was also there was a focus also on doing data simulation sensitivity studies. Work package 6, the main activity in work package 6 was the submission to the first global stocktake. Again, many modeling groups across Europe participated in this effort. And of course, there was also, an effort to, and then the next step is, of course, doing this again when the next global stocktake comes. And so on this, there is some work going on to kind of improve the data simulation tools that we used in the first global stocktake contribution to do better next time. And then work package 7 was about observations. So here there was some survey-based activities which was used to basically try to understand within the project what people thought were the needs and how these needs could be met. There were like interviews done and surveys to try to understand what was missing and how the things that were needed could be met. And the other activity inside this work package was developing, using the Internet of Things and thinking of, if it's possible, using the Internet of Things to try to assimilate low-cost observations for greenhouse gases. And finally, work package 8, which was the closest to the users, let's say. So there were activities, for example, in trying to reconciliate the output from the project with the inventories, emission inventories, so all the emissions resulting from the inversion run in the other work packages, how they compare against the inversions, the inventories. And then there were also some other activities like publishing a catalog of, for example, this is for hotspot detection on a website so that these results could be shared with the wider community. And that's it. So, thank you.
Thank you very much, Luca, and right on time, so you succeeded. Any questions for Luca on COCO 2? I don't see any raised hands, so I assume everything was very clear. Next up, I welcome to the stage Adrian Martinez, who will be guiding you through the details of the Catherine project.
So, hello everyone, I'm Adrian Martinez from LSC, and I will present you the Catherine project, which is quite a new project. It just began in January of this year. So this is, as a previous project that was presented just before, kind of an overarching project that aimed to improve CO2 MVS. And I think it has quite an explicit name. Catherine is carbon atmospheric tracer research to improve numerics and evaluations. So, as I said, the main aim of Catherine is to improve CO2 MVS. You've seen this graph today many times, but I will just go quickly then. So CO2 MVS take observation and prior information about emissions that are integrated to produce consolidated emissions. And it has been pointed out that the main source of uncertainties in this system is the integration part and mainly the transport part, the transport model. And the uncertainties come from many aspects in the transport model. They can come from advection scheme and resolution. They can come from convective transport, from parameterized processes like turbulence, and also from NWP analysis. So the aim of the Catherine project is the main one is to evaluate and improve numerical schemes for tracer transport in CO2 MVS. But as it's quite a basic topic about transport, it can be applied to more projects than CO2 MVS that use transport. And we divided this objective in many steps. So deliver improved methods to simulate reservoir tracer transport, impact the assessment of improving tracer transport for the quality of the estimate of CO2 and methane fluxes. So we also want to develop test beds for global and local models that can be linked to field campaigns. We want to test development in the parameterization of unresolved processes, so sub-grid scale processes like the blunt mixing and convection, and also develop accurate metrics for tracer transport using local or global scale and observation and different tracer. So we don't have to rely only on intercomparison of models. And all of that should lead us to provide clear recommendation for the CO2 MVS regarding the evaluation and the quality assessment of tracer transport. So, and all these objectives are divided in several work packages. On this graph, we have on the horizontal axis the scale of the model from global to local model, and on the vertical axis the different processes, resolved and unresolved processes. So for the work packages, we have work packages 1 and 2 focusing on aggregation scheme in global models, work package 3 and 4 focusing on very high resolution in local models, especially for hotspot emission. Work package 5 and 6 are focusing on parameterized processes like turbulent mixing and convection. And the last 2 work packages will apply to all these aspects, and they are about developing metrics to evaluate the transport of tracers. And all these work packages are shared along the Catherine Consortium, which is composed of 8 partners for 4 different countries. So France, Netherlands, Germany, and Finland, and also ECMWF. And it is composed of people from various backgrounds, some NWP scientists, carbon cycle scientists, also atmospheric chemistry scientists. So it provides the project with a wide range of expertise, notably numerical methods in atmospheric inversion systems, in parameterization of unresolved processes in transport, in intercomparison projects, and also in research to operation transition. So now I will go and explain a bit what is in all those work packages. So firstly, work packages 1 and 2 on advection. These work packages are really focused on the IFS model, the advection scheme of the IFS model, which is a semi-Lagrangian model that has some advantages. It's very good at for transporting many tracers, but it has also some drawbacks, notably for mass conservation. So this advection scheme need a limiter to prevent some overshoot and undershoot error with the model. And you can see on the top right graph, on it we have on the horizontal axis the time, and on the vertical axis the mass conservation error. We can see that with the limiter that fix some aspects, we have a worse mass conservation error than without the limiter. So the model has also a fixer to try to resolve the problem with mass conservation. And on the bottom graph, which have the same axis, you can see all the different setups that are experimented with some version of the limiter, some new version of the limiter, and with or without the fixer that try to fix the mass conservation error. So there is a lot of things to improve there, and we have planned things to do for that. So first thing is to develop test cases from very simple case to more realistic case to really assess the error from the mass conservation. We plan to do some OSSs to assess the error. So there are research to improve the COMAT semi-Lagrangian advection interpolation from meteor funds that is used in CAMS, also to improve and develop tangent linear and adjacent specs in existing advection scheme. And we also want to try over advection scheme that can be adapted to the IFS. So MP data, for example, that can help with mass conservation, but may be challenging to implement, or, for example, discontinuous galactic semi-Lagrangian transports that can also bring some enhancement to the advection. So for the next work packages, the work package 3 and 4 focused on local model. We want to focus on looking on emission hotspots and simulation of plumes, and to see for that the influence on boundary conditions, perform some sensitivity studies, and also doing intercomparison of some high-resolution models that are listed in the table on the bottom left. And all these models have very high resolution. We are talking about MIFA resolution on the horizontal and vertical, and 1 second resolution on the temporal. And on the top right plot, we can see what is the main aspect that is good about high resolution is we got very detailed plumes. On this plot, we compare on the left a coarser resolution and a higher resolution, and there is a strong difference between the two simulations. And the other thing that is important to look at is the vertical distribution of the plume that is illustrated in the other plot. So for the next work package, 5 and 6, they are focused on parameterized processes, so sub-scale processes in global models that cannot be simulated as is and need to be parameterized. And so we want to look at that to try new developments, to perform comparison, notably with field studies, like you can see on this plot, which is an example of a field studies that I compared to model. And on this example, we looked at the vertical distribution of the transport in the model. And there are a lot of processes that are parameterized, and they impact a lot the vertical transport. So there is the transfer troposphere exchange, the long-range transport in the troposphere, some boundary layer ventilations, the diurnal variability, and also the surface and atmosphere exchanges. So, and in order to support all these work packages, we have the last 2 work packages, 7 and 4, that aim to develop new metrics to quantify the errors in transports. So we do not have to only rely on intercomparison and have some metrics to look at. With those metrics, we plan to perform some intercomparison between global models. So global model within the Catherine Consortium, which is IFS, LMDZ, ICONAT, and TM5, which I will present a bit in detail just after. But we can also include other models from the transport community. So we plan to do an experiment on a 2-year period with a 1 month spin-up, and we choose some tracer to transport. We choose CO2 and CO2 from fossil fuel emissions because we focus on CO2 MVS, and that are the tracer we aim to improve the transport of. But we also choose SF6 and radon because they are quite nice tracer when you study transport. Then they have nice property for that. And there are also real tracers. All of them exist in real life, so we can compare with some observations. And for all those experiments, we will use some boundary condition, so prescribed from reference surface fluxes and emission data sets, and also some boundary condition from ERA 5. And we had to choose what we will look at on the output of this experiment, and we decide on some fields. So maybe the most important one are the field directly linked to transport. So the time-integrated, vertically integrated northward and eastward tracer fluxes that are illustrated on the top right figure, but also the time-integrated and vertically integrated tracer divergent flux, which is represented on the top right figure. So these 2 quantities can help us compare the difference between the model in the transport when the transport converges the tracer, when it comes from, when it goes. So, and there is some details about the model. We want to compare the global models. So there is 4 models, but they can be quite different. They're all from different institutes. They have somewhat different horizontal and vertical resolutions. And also, some of them are online models, some of them are offline models. So this is a few models, but a wide range of setups and different simulations. So, with all of that, what are the benefits we expect with the Catherine project? So, The first one is we want to develop and test new innovative methods to improve accuracy of mass conservation for CO2 MVS. So something that is directly applied to CO2 MVS, but can be applied somewhere else. We want to quantify the added value of high resolution, notably with local models. So, and we want to enhance existing link between NWP and enhance the knowledge transfer between NWP and air quality modeling, because we think we can both benefit from such transfer of knowledge. And finally, we could engage with the international community to participate in a tracer transport experiment exercise within the Transcom program. So yeah, and maybe the thing to get out of that is that all these objectives will benefit CO2 MVS, but can also benefit other studies that use tracer transport. So that's all for this presentation. Thank you, and I would like also to thank all the partners that are, hopefully all of them are their logo in this slide, and also to thank the European Union that grant funding to the current project.
Thank you very much, Adrien. We have perhaps time for questions, comments from the audience, if any. No? Okay, good. Then we'll move on to our next speaker. It's Auke Visser from ECMWF, and he will be telling you all about the third project that is supporting the preparation of CO2 MVS, which is called the Corso project. Auke, the floor is yours.
Hello, good afternoon. So indeed, my name is Auke Visser, and I work at ECMWF since the beginning of last year, and I'm employed working on the Corso project. So the Corso project is also a Horizon Europe funded project that runs for 3 years, and we're now about halfway through the project, which means that besides an overview, I can also already start sharing with you some exciting first results from this project. So this one is very familiar to all of you by now, but actually bear with me, because in 1 or 2 slides I will provide a short proposal for an update to this one based on the Corso project. But the Corso project itself is very much focused on the left side of the CO2 MVS, which is how we can improve our integration and modeling systems with additional observations and also improved prior information to provide hopefully even better estimates of anthropogenic CO2 emissions. Corso stands for CO2 MVS Research on Supplementary Observations, and what it actually tries to tackle is some scientific challenges that relate to isolating the anthropogenic signal based on variability in atmospheric CO2 that you can measure either from space or with in situ measurements. And the way that we try to do this is first of all, by using observations of co-emitted species, so CO and NOx, that are emitted alongside CO2 in combustion processes. This will hopefully get us a better grip on really the anthropogenic component of CO2 emissions. And the second one is to use fossil fuel tracers. So we have radiocarbon, which is a naturally occurring isotope of CO2, and APO, which is a tracer based on atmospheric oxygen. So the idea being that where CO2 is emitted, oxygen is actually consumed, and where CO2 is taken up, for example, in the biosphere, oxygen is actually released. So this can actually provide us some better grips on the fossil fuel versus the biospheric fluxes of CO2. And on the bottom of the slide, I list all the 16 consortium partners in this project. So here I show you a very, very concise overview of what each work package tries to do. Work package 1 is really focusing on the prior information that we have by delivering improved data of emission factors and also emission ratios between CO2 and the co-emitted species, and also very importantly their uncertainties. So this is in itself already very important information, but also it's an essential component of the data assimilation systems that we are working with. So work package 2 is then using the output from work package 1 to build or improve the emission inversion system so that it can actually use observations of, for example, NO2 columns or carbon monoxide columns to constrain CO2 emissions better. Work package 3 is very much focused on the fossil fuel tracers to separate biogenic and anthropogenic emissions. And in work package 4, the team is working on constraining the carbon cycle variables better by assimilating additional satellite observations of soil moisture, leaf area index, fluorescence, and also biomass. And across work package task is to also deliver specific recommendations for the operational implementation in the CO2 MVS. And what I already promised is the update to this slide. So I think if Corso is successful and this all works well, we can add additional observations of the co-emitted species, the tracers, and also the natural biosphere. And also on the bottom right, the improved estimates, improved prior information, which then, with also improved integration and modeling, can hopefully improve CO2 emission estimates. So now in the remainder of my talk, I will go through each of the 4 work packages and show you some first results. So some exciting outcomes. So work package 1, the first thing that I would like to show is the global maps of emission factors and also their associated uncertainties. So you see on the top left a figure that shows emission factors for road transport in different countries in the world. And you see already that there's quite a bit of difference. But then on top of that, this is only one number, but we would also like to quantify how uncertain this number actually is. And that's what you see on the bottom left. This is an estimate for the uncertainty on one of those emission factors for one country, in this case, Brazil. On the right, you see developments on the point source database that was already being worked on in COCO 2. But in this case, this point source data set will be improved, and also with a particular focus on also co-emitted species. So that's what you see on this figure. And just to note that the different colors for all these dots refer to different types of emissions. So work package 2, using co-emitted species in data assimilations for emission inversions. The end goal of this work package is on the bottom of the slide, and it's namely to assimilate data-driven estimates into the IFS to constrain CO2 emissions. And I will walk you through this. Part of this work package is focused on developing methods to estimate emissions from point sources using satellite observations in a data-driven manner. So they use, for example, individual orbits. In this case, on the top left, what you see is NO2. You see a plume coming from a power plant in South Africa. And this team has developed a method to estimate the emissions based on this plume directly from the power plant. So if we want to also assimilate these sorts of data into the IFS, we also need to think about NOx chemistry, which is computationally too expensive to run the full IFS chemistry scheme as part of the CO2 MVS. So there's also a team working on speeding up NOx chemistry by developing a surrogate model based on machine learning. And some results are shown on the top right, where the full chemistry scheme is compared to the machine learning based version. And the relative difference is shown on the bottom of these 3 panels, and it's showing actually relatively encouraging results. So this is already something really nice that is coming out of the project. And the last important component of this work package is that we also need to we need to really update our inversion system, and especially the prior error covariance matrix. And we need to do this to transfer information in space in the data assimilation system. But what we would also like to do is to add a temporal component to this, and also a cross-species component. So and for these kinds of things, we are really relying on the data coming from work package 1 to calculate the metrics, some of which you see in these figures on the bottom, for the B matrix, the prior error covariance matrix. Work package 3 is then focused on the fossil fuel tracers. And basically their research question is to investigate the added value of a dense network with high temporal frequency of observations of all these tracers, and whether this can aid in better separating the fossil fuel and the biogenic signal. So for this, they are currently performing an intensive observation campaign. Yeah, they're testing a high-density observation network in Europe. So you see the sites on the top left. And at the same time, they're also compiling a database with global observations from other measurement laboratories in the world. And that's what you see on the right. So that is the observational component of this work package, but there's also a modeling component. So there are developments in the forward modeling and also the inverse modeling of these tracers to actually put better constraints on CO2 emissions. And this is just a comparison between a regional and a global model in representing APO, atmospheric potential oxygen, at the site in the UK. And then lastly, this is the last work package is focused on using, well, yeah, like the novel use of satellite observations to constrain the biosphere. And for what they've been doing so far mainly is developing observation operators so that we can assimilate different streams of observation into the IFS to constrain the water cycle and also the carbon cycle. So on the top you see backscattering coefficients in a scatter plot where basically they developed a machine learning model to predict the backscatter, and then they show how this compares to the actually observed backscatter in the training period and also in a testing period. And you see actually that the performance is quite similar and also relatively good. So this is quite encouraging. And on the bottom row of plots, you see something quite similar, but then this is for sun-induced fluorescence, which is supposed to provide a direct measurement of the photosynthesis process. And this can, of course, also help us to put constraints on CO2 exchange in ecosystems. So this was just a very brief overview of the Corso project. So with that, I would just like to thank you for your attention. And yeah.
Thank you very much, Auke, for this excellent overview. Questions, comments from the room? No, everything is very clear. Okay, then I can invite to the stage our next speaker. That's Zoe Pascalidi, who will be telling you about the CAMEO project.
Hello, everybody. I hope that you can hear me. Yes. I'm Zoe. I also work in ECMWF, and now it is my turn to present you the CAMS evolution project, the CAMEO. After its 1.5 first year, the presentation is a joint work from all the working groups of the project, and I would like to thank the project, the working package leaders for their contribution. So, CAMEO is an Horizon Europe project, a large consortium of 22 European institutes to support the developments of CAMS in air quality modeling using the latest technological achievements. The main focus is the implementation of, is the assimilation of aerosol and reactive gases observed from traditional and new satellites. The main goal of CAMEO is the improvement of the operational services and products of CAMS. The project has 3 working packages that are dealing with the data assimilation and the use of the new satellite data, and all kind new of observational data, and 3 working packages that are dealing with the uncertainties improvement. The project has a large series of deliverables, but the purpose of my presentation is not to list all of them, but to give an overview of our work and our field, working field, and highlighting some of the first results. So firstly, we will see the first 3 working packages that deal with data assimilation. So, and the first work package has 3 main tasks, and the main aim is the improvement of the aerosol assimilation in CAMS. So, the project first exploits the visible radiance radiance assimilation of aerosol applications by linking the CAMS aerosol system with the RTTOF. And actually, all the technical updates are there, and the first runs with the forward model shows that the implemented method give us better results, and we can further have updated information with the joint use, for instance, of aerosol and cloud radiances, instead of only using the aerosol radiances that give us, that are full of these red spots that are the clouds. So the second part of this work deals with the alignment of the aerosol representation in model and the retrievals. As in each case, different assumptions, a lot of different assumptions are used. The development method gives a synthetic retrieval for optical properties that look to be beneficial for real data applications. The last task of this working package deals with the the development of an offline optical operator for the IFS that avoids the difficult modeling and only looks of the optical representation of aerosols. The first version of the OPS, as this operator is named, is available, and it computes aerosol parameters offline. And actually, the first comparisons with the model with the IFS are show that they have a great agreement. Now, I'm going to the work package 2, which is actually the work package that I am working on. Here we work on the assimilation of satellite data and the development of inversion techniques for the global IFS. The first task, The first task, that's actually my work, deals with the preparation of the use of all upcoming satellite retrievals with a focus on the geostationary high-resolved air quality data from GEMS, TEMPO, and later for S4. We have started using the GEMS near real-time data. We get the data we acquire, we convert them to the proper format for the IFS, and we routinely monitor GEMS and O2 and ozone in the operational CAMS suite for the cycle 49R1. The first analysis of the GEMS NO2 data show that the data have large biases comparing with the model and the Tropomi NO2. For instance, here we see the analysis departures from NO2 for GEMS and Tropomi, and it is clear that there is a huge bias. That's why we cannot assimilate at the moment the GEMS NO2 data. We wait for the new version of the data provider that it looks like they deal with the bugs. But this is not the case for ozone, that the agreement with other ozone satellite data is in good shape, so we have performed assimilation experiments for GEMS ozone. And here is an example of ozone profiles, a bit busy, focus only on the yellow and the blue lines, where blue has the GEMS ozone assimilation, and it looks like there is an impact in the troposphere by assimilating GEMS ozone. The results are preliminary. We are on thorough validation. Another task of the work package 2 is the development of a new super observation software that is based on the improvement and the modeling of the observation uncertainties. The software is already developed and implemented in the IFS, and we are on the phase of validating it with long runs. Further, the work package 2 works with implementation of an inversion capability for biogenic emissions. Here, a simplified chemistry for Tropomi formaldehyde is developed together with a tangent linear adjoint of this version. It is actually in good agreement with the full chemistry. So if you see here the red and the pink lines. Further, a new online emission system for biogenic VOCs is developed that replaces the offline emission inventories. The last part of these tasks deals with the development of a weak 4D VAR that is implemented for the stratospheric ozone for CAMS and NWP in ECMWF that allows us to go from the assumption of the perfect model to the acknowledgement that our model has errors, and we try to model them. For this purpose, a model error covariant matrix is developed, and for the first application, it looks like the analysis and the background error with the weak constraint are improved in comparison with the operational scheme. Going fast a bit further to the work package 3, here we deal with the enhancement of satellite data assimilation in the for regional models. The regional models are prepared for the use of the geostationary data from Sentinel-4 by first developing their system to assimilate Tropomi and Cobra products. Here, for instance, Here, for instance, is an example of the application of the new updated observational operator for SO2, Cobra SO2 data, where we get more detailed and high-result information identifying emission spots in the local scale. Further on this part of the project, the groups work on the assimilation of aerosols. Here, a large, to improve the aerosol analysis, an e-profile network is developed with different kinds of instruments, LiDAR and sailometers and so on. And it is assimilated, giving good correlations and also more detailed information of the vertical structure of the troposphere. Last part here of this working package for the regional modeling, the groups work on the assimilation of the IRS and as a preparation also for the S4 data. Here, OSIs are carried out to anticipate Sentinel-4 and IRS data fluxes. The first results give a significant reduction of ozone and CO2. For instance, here, whatever is with blue line is a positive impact that the method gives, red a negative, and the yellow is like a significant one. This work is still on evaluation. So now we go on from the 3 working packages from the data simulation to the next 3 that deal with the uncertainties. And here the first working package, the working package 4, aims to quantify the uncertainty of CAMS products by employing machine learning methods for UV data and aerosol deposition. The ground stations are the ground network is expanding, giving us much larger data sets, but we can say with a controversial quality and with comparison with the operational ground stations. And here comes the whole uncertainty study. If we go further to the aerosol deposition, here a large series of new data are tested in the IFS ensemble model, perturbating different parameters each time in order to come up with uncertainties estimations for these parameters. I think we discussed already today some part. So next, the uncertainty of emission products is the main work of the work package 5. Here, the job is split in 4 parts. First, we have the improvement of the uncertainty emission temporal profiles, where different emission profiles are conducted for on temporal weight with different weight factors. For instance, for hourly, monthly, or weekly data for the regional and the global. Updating with this method the respective CAMS pollutant factors. Second part is the improvement of the uncertainty on global isoprene emissions. Here, by updates in the Megan model, with playing with Megan model with different input parameters, we come up with a minimum and maximum of each parameter, giving us a range of uncertainty for each one of them. And thus, further, we can have the range uncertainty of isoprene. The next part deals with the improvement of the anthropogenic emissions uncertainty for the global and the regional. And for instance, for the regional emissions, we have the development of PM emission uncertainties per factor, per country, and also taking into account the different grids. And we have a more detailed information. The last part of this working package works on the development inversion emissions for NO2 and greenhouse gases, which are, we can say, in good agreement with the model, as we can see here with the comparison for the different cities. And the last part of the working packages that deals with the uncertainty estimates is the working package 6. Here the groups work either on the ensemble for the global forecast, either on the modeling for the different policy products. For the sake of time, I won't be on details here. I just want to highlight some examples of the propagation of emission uncertainties in different, in the different cases. For instance, for the global forecast, with the use of different combination of ensembles, we get the first estimation of the propagation of each kind of the uncertainties for its region, its date and species, and so on. And the group has also gone on with the development of local scale variabilities for EU cities. And with this, I come up to my last slide. So the project is in his middle phases. So far, the 26% of the deliverables are done. And by the end of the year, more than 60% will be delivered. And all the information, updates, results, and contacts can be found on our website. And thank you very much.
Thank you very much, Zoe, for this status update on Cameo. Questions from the room? If not, in view of time, I propose that you can approach Zoe after the session. And then I invite to the stage Paul Hamer. He will be guiding you through the results of the SEEDS project. It's a Horizon 2020 project that ended in the end of 23. Paul.
Thank you. Yeah, my name is Paul Hamer. I work at NILU in Norway. Yeah, I'll be presenting the SEEDS project. SEEDS, the acronym stands for Sentinels for Emission and Deposition Service. So there was a large consortium, there was a large number of people that contributed to the project. So we had NILU, we had KNMI, we had BIRA here in Brussels, CNRM, Météo France, Surfax, now Manueli is now at BSC in Barcelona, and also we had Lobelia contributing to this. So the SEEDS project was aimed at trying to explore potential developments and add-ons to the current version of the CAMS regional service. And there were three main goals, three things that we tried to explore. One was trying to develop top-down emission estimates using satellite observations for NOx, ammonia, and isoprene. And then there was another part of the project dedicated to trying to look at land surface modeling and how that couples to dynamic simulations of vegetation. And then using a simulation again of satellite observations to try to then improve the model to get better estimates of deposition and also bottom-up fluxes of BVOCs, of isoprene, and other BVOCs. And then lastly, another component was trying to develop a new data assimilation algorithm that could be put in an open library that then could potentially be used by the other groups in the CAMS consortium. So yeah, we developed a range of products, which I'll present in the next couple of slides. And then we tried to also explore the potential of these, what is the value of these products, and then trying to look at how that might potentially fit into the operational chain within CAMS. Yeah, and then once we had all these data products, they're available to the public. And then we've tried to engage various possible users outside and beyond just CAMS. So people in the agricultural and industry sectors who might be interested in emissions. So there were a range of products, as I've just quickly mentioned. So we have the top-down emission estimates of NOx, ammonia, BVOC, and also carbon flux. So for anthropogenic NOx, we have three different products, two over what I call limited Europe. So it's a kind of cutout over the central part of Europe at both 0.2 degree resolution and also then there's a zoom over the Netherlands and the Ruhr at 0.05 degree resolution. And the coarser spatial resolution products are available at monthly and daily time resolutions. We also have ammonia emissions, which are based on using the CRIS satellite observations. Then we had top-down carbon flux at 0.1 degree, soil NOx emissions, and then top-down isoprene emissions. And then in the component of work using the land surface modeling, we had the leaf area index analysis, which is based on the assimilation of leaf area index observations. Soil moisture analysis, again, derived from the assimilation of leaf area index. Then we had the deposition fluxes, which come out of the land surface model, which are linked into the improvements we're getting from doing the data assimilation. And then, again, feeding in the outputs from the land surface model into the Megan 3 model, we're getting an emission inventory for BVOCs that's independent of the top-down constrained emissions from BIRA. And then lastly, there's now an open source algorithm for assimilation for 4D NVAR, which Emanuele has been developing. And that, he's been testing that in the context of trying to improve CAMS forecasts. So, yeah, focusing quickly. So the first objective, again, linking back to the previous slides, we had anthropogenic emissions of NOx, ammonia, and biomass burning. So for the NOx and ammonia emissions, that's coming from the DEXO algorithm being developed by KNMI. And then for the BVOC emissions, sorry, the isoprene emissions, I should say, that's coming from the work of Jenny Stavrakou at BIRA using the Magritte model. And out of that is coming NOx from NO2 from Tropomi, ammonia is coming from CRIS, and then we have also a carbon flux from biomass burning derived from formaldehyde observations from Tropomi again. So in terms of, these are just some quick pictures showing the results for the NOx emissions. These are estimates by country compared to some of the other data sets available. You can see the comparison with CAMS and the HTAP and LRTAP emission inventories. And these are the maps from DEXO down in the bottom showing what the different domains. That's the Zoom domain over the Netherlands. And this is the what I call limited Europe domain here. It's not the full CAMS domain. And what we kind of got out of this, there are different advantages and some limitations. So I'll sort of start off in terms of location and resolution. So yeah, the spatial resolution of the emissions, apart from over the Zoom domain, was limited to 0.1 degree, which 0.2 degree, which is coarser than the CAMS resolution. So that's a bit of a limitation. It was difficult to apply over the whole globe and not over the full CAMS domain. And this is just limited by the availability of observations and the computational costs of running the algorithm. But what we get out of this is we're able to catch year-to-year variations in emissions. Also, we can get an estimate of the monthly and weekly variations in emissions. And we hope that when Sentinel-4 comes along, that will further improve, and we'll get information on what's going on within the day in terms of emission variability. And then we can also check the emissions that we're getting out of DEXO against known point sources, and trying to see when point sources are either being turned off or when they're turning on. Yeah. So then, yeah, we can do an evaluation against other emission data sets. Yeah, but I think there needs to be maybe some further work to maybe check against other chemical species to see if we can evaluate the emissions that we've got. Okay, so I talked about the BVOC emissions. Within that, we're also getting the soil MOX emissions. That's also derived from the work of KNMI. So we've got, again, inversion technique based on DEXO and Magritte. Yeah. And then we also have a bottom-up emission estimate that's coming from the land surface modeling work that I described earlier. Okay, so yeah, this is just a quick a map of what the emission data set looks like from Magritte for isoprene. And you can see that according to the model, and this is really strongly constrained by the observations, a lot of the isoprene emissions are concentrated in the southern areas of Europe. And we've got good confidence in the Tropomi formaldehyde data set that it correlates very well with daily maximum temperature, which is really a good indication that it's a good quality data set. And the data set, one of the great things about it, it's allowed, we've had a lot of cooperation between the top-down and bottom-up communities already. We've had a lot of discussion going on, trying to review and verify the data to gain insight on what's going on. So that's one of been really the positive outcomes of the project. And unfortunately, it's not possible at the moment to run it globally because it's computationally too expensive. So one piece of work that I understand is being explored within Cameo is to come up with a simplified chemistry scheme to try to do this. Yeah, we've had a lot of success with the land surface vegetation modeling, and that's going to be further. We hope that there might be some opportunities to further test that within CAMS. But there is a bit of a concern that the version of Megan we have used, that it's difficult to really show the added value that's coming from the soil moisture data that we derived. So, okay. So this is an overview of what the land surface model component looks like. So the input to this are observations of leaf area index from 2 different sensors, so ProbaV and AVHRR. This goes into the Surfix land surface model. These other inputs, we're using the ECMWF IFS meteorology that's the same as what's being used in CAMS. And then out of this, we get an assimilation analysis and the open loop, the free running model. And then that's used to derive deposition velocities for both, we get out of that then assimilated analysis for deposition and the free running deposition results. Again, we also get the BVOCs, which was previously mentioned. And again, both in analysis and open loop mode. One of the really positive things we've done is we've compared the leaf area index. If you look at the bottom image on the right, we compared the leaf area index from the land surface model after the assimilation to observed SIF from Tropomi. And we get extremely high correlation over large areas of Europe. And it was interesting because we actually initially thought we'd get better correlation against GPP, gross primary production, because SIF is supposed to be an indicator of photosynthesis. However, we actually get much stronger correlation with LAI, so yeah, we need to investigate that further. But it does indicate that we've got an independent observation showing that the LAI coming out of the model is of good quality. So out of this work, we're hoping that this provides a potential proof of concept for how a land surface model could be used to support the regional modeling efforts, that really trying to improve the leaf area index as an input going into different streams of for deposition, and also the BVACs could have potential value in the future for CAMS. And we're working with some groups within CAMS to try to explore the value of this further. Okay. So this is quickly about the open source data assimilation algorithm. So this is the 4D-NVAR algorithm. It's now freely available. You can get the algorithm. I'll show you the link at the end that goes to the seeds page where all of this is available. Yeah, and it's extremely successful at reducing the model error, and we're hoping that when Sentinel-4 comes along, that this will be of great value to try to improve the models even further. Okay, so to try to test all of the data products that we've developed, we came up with a strategy to how to do this, and this is the initial strategy we had is based around thinking what products will be available when in terms of the timeline of the chain of production. And obviously, because if you do an emission inversion, you get the observation, I think, in the afternoon. So you can't use the derived emissions from the forecast, which is run at midnight for that day. So you could probably only use this in an analysis mode. So that's the reason why we've done that. And then we've later tested all of the products in the forecast mode. I'll explain that shortly, why. And the reason is that it's actually extremely difficult to improve the analysis, the CAMS regional analysis, because it's already very good, because it's being updated by the surface observations. So when we've tested our products in forecast mode, we're seeing a lot clearer difference between the model versions, and we're seeing an improvement there. So then, yeah, I'll talk a little bit about what this might mean in terms of how this might go forward into CAMS in the future. So, yeah, because of the forecast has got these temporal constraints, it's really challenging to introduce the data into the stream. But the top-down emissions may have a value of evaluating the emissions which are going into CAMS, sort of like a real-time evaluation of the emission products. There may also be a possibility of including those emissions in a kind of analysis that's maybe run a few days after the forecast. That's one possibility. The 4D NVAR algorithm is open for use within the CAMS community. And yeah, the land surface model, it is actually possible to run it simultaneously or just slightly before the forecast and get a forecast from that, which could be used within the CAMS production chain if groups were interested. One limitation is a lot of our testing was done with just the mockage model, so that's just one member of the CAMS ensemble. So it would be useful if people were interested to test it in more of the ensemble models. Okay. So once we put all our data into this data portal, we've engaged different user groups, and we've tried to kind of get feedback. So we've been talking to emission experts, local authorities, and then getting them to evaluate our data. Yeah. And yeah, so some of the lessons learned from this are, for instance, that it's quite difficult. It has been challenging to develop the right working relationship with the industry. But there is, when we look at our data, there is really a good potential for informing their emission estimates. And I think it's probably the biggest value of this is in the emission verification work that's going on in Europe. Yeah, also the ammonia emission information has been really valuable, and we're trying to work with the emission groups that are estimating emissions at very, very high resolution in Denmark. So we're working with the modelers from DEEM on this. Yeah, and we're also trying to test the leaf air index products within different types of modeling activities. Right. Okay, so yeah, just in summary, seeds has, I think, really shown what the values and capability of Sentinel 5P is in terms of improving the spatial resolution and the temporal information and identifying missing sources. It's been really valuable for this. We've got 18 different products which are now available for use in the broader scientific community. We've produced algorithms that could be potentially used in Sentinel-4. Using Sentinel-4, sorry. The top-down emissions have shown great capability to try to review and validate bottom-up emission estimates around Europe. And the land surface model approach that we've used is providing a proof of concept for a potential way forward to do dynamical vegetation simulation modeling and land surface modeling as a way to inform the improvements in the CAMS regional models. And yeah, we're working. It's an ongoing work with the CAMS community to test these products and yeah, doing ongoing user uptake activities. So I'll just leave you with a slide showing the CAMS data viewer. Yeah, which is available at this link here, and you can just gain access to the products and have a look at them if you want.
Thank you. Thank you very much, Paul. I can maybe add to that just only today the SEEDS team published on the website as well a very nice publication with an overview of all of the project achievements. So I invite you to check that out on the project website. Questions for Paul? If not, I will introduce our final speaker. We have Rose Chloe Meyer from IGEOS, who will present to you the CAMERA project.
Hello, thank you for the introduction. So, I'm waiting for the slide. Okay, thank you. Okay, can you hear me? Yes. So, as you said, I will present the CAMERA project, which stands for CAMS Aerosol Advancement. So CAMERA is a Horizon Europe project, and in particular, it's part of the project for the improvement of CAMS product. In CAMERA, we work with different regional models and with the global model, and all the developers and operators of the regional models are involved in the project. In total, this represents 15 different partners. So the main goal of the project CAMERA are the following. The improvement of the aerosol modeling for the regional models and global model, the assimilation of new sources of data, a better representation of the secondary organic aerosol, and an improvement in the interfaces between the regional and global model. So CAMERA is a 36-month project, and it has started in January 2024. It is composed of 12 work packages. In fact, this is a 6 group of 2 work packages, and each work package lasts 18 months. In particular, there are 2 project management work packages to coordinate the different parts of the project and the different partners. The different work packages are connected because some results obtained in some parts of the project will be used later in other work packages. I will now describe in more detail the different work packages and give a few results. So the first work packages covers the data assimilation and the flux inversion. So data assimilation is highly efficient to improve the quality of the simulation. However, in the IFS, the model uses the assimilation only on the AOD and assimilate a total mixing ratio with limited information on the speciation of the aerosol. In addition, the model uses a total column quantity with no information on the vertical profile of the particles. The idea here is to improve these 2 points by using data assimilation with LIDAR and ceilometer to improve the vertical distribution, and with infrared data assimilation to improve the speciation. The other part of work packages 1 and 2 is on the flux inversion for the dust emission. So dust emission are highly dependent on the model used due to large uncertainties on the inputs. So the goal here is to develop and provide a new reference dust emission datasets. Now moving on to work packages 3 and 4 on the model representation of the aerosol. So currently the IFS model uses a Bunn-Bilk scheme representation of the aerosol. And the idea here is to use instead a model called the M7. So with this model, the representation of the aerosol will be improved. In particular, the size distribution will be given in more details, and we will also have more information on the internal mixing of the different chemical components. Another part of work packages 3 and 4 is the coupling between the M7 model with the modeling of inorganic aerosol. So for now, the M7 model has been implemented in OpenIFS cycle 48R1, and the implementation in cycle 49R1 is in progress. The next 2 work packages focus on the online emissions and the deposition. So the first part is to improve the dynamical emissions for the primary aerosols like sea salt, desert dust, and biomass burning. and also the ammonia precursors. For this, we will test different new methodologies, like for example, a deep learning method using a neural network, and also new representation of the agricultural activity will be developed. Another part of this work packages is a dry deposition. So concerning the online emission, a deep learning technique has been developed using neural networks for the emission of the sea salt aerosol. Here we can see a result for a few days. So this kind of deep learning approach will also be used during the project for dust emission. In addition, some results using a chamber experiment will be used for the sea salt emission. Concerning dust emission, in addition to the deep learning techniques, the implementation of the dust emission for high latitude will be done, along with the implementation of a gridded version of the Nord-Street broad dust scheme. Finally, the fire forecast system will be implemented and evaluated. The second part of work packages 5 and 6 is on the interactive ammonia emissions. So here is an example of the forecast of ammonia emission for cycle 48R1 and 49R1 compared to the observation in black. And we can see that the curves are quite different due in particular to the fact that the ammonia emissions depend on the period of the year. So the idea here is to improve the forecast by implementing new ammonia emission models. The models will be evaluated against observation and also against inversion products. The last part of work packages 5 and 6 focuses on the dry deposition. So dry deposition study will be done at the level 0D, and different schemes will be compared. So 5 regional schemes will be compared, and 3 schemes in the IFS. So all the different schemes will be compared and evaluated against in observation. Next, the work packages 7 and 8 focus on the secondary aerosol. So the secondary organic aerosols are produced from precursor gases. Here is an example on the figure of a different simulation in red compared to the observation in black. So on top it is for every period of the year. On the bottom left it's for summertime, and on the right for winter time. So we can see that the different model underestimate a lot the secondary organic aerosol, in particular for the winter time. So the goal here is to improve the models, and for this work will be done on the emission system, but also on the modeling of the organic compounds and the biogenic aerosol. So for that, different methods are going to be tested and compared. Another part of work packages 7-8 is the implementation of a primary biological aerosol in MEP. So this is a result from Met Norway. This result is for the fungal spores, which have a significant impact on the PM10. So the observations are given in blue on the left and the simulation in yellow. And we can see that the results are quite encouraging. So the last work packages, the goal is to improve the consistency between the regional and global models. So the first idea is to compare the different models. An intercomparison of the regional model has already been done, but here the idea is also to include the global model IFS. So for this, it is necessary to use a similar emission, and hence to merge the regional emission into the global modeling. So all the different models, the 11 regional models and the global model, are going to be compared and evaluated. So the second part of work packages 9 and 10 is on the matching boundary, is a matching of the boundary condition. So when a regional model is used, it is necessary to define the condition at the boundaries of the domain for the interface. And for this, data are taken from the global model. A study will be done on which data it is better to use, which parameters, and how to integrate them in the global model. And this includes also the resolution needed for the interfaces. So here is a result of a first comparison. So it's the global model, the simulation of PM 2.5, compared to the observation in blue. So the difference between the two curves is that in the red curves, we use the global emission with global model. And in the green curves, we use the regional emissions on Europe. So we can see quite some differences. So it's necessary to use the same emission in order to compare it with different models. Okay, so to finish, Camera will have a website which will be soon active, and the link is given here. Thank you.
Thank you very much, Rose-Chloé, for the presentations. I try one last time. Any questions for the presenter here? If not, then all remains for me is to wrap up this session. I would like to thank once again our 6 project speakers, and would like to thank all of you for your attention. And I believe I can pass on the floor to the next speakers for the final conclusions. Thank you very much.
Hello again. So, for the conclusions. First, thank you for another excellent General Assembly. My very short conclusion is that there is still so much going on in CAMS, and there's more going on every year. And the General Assembly really provides a good overview of everything, all the work, from user interaction activities to work on dust and air quality services, including applications for the energy sector, to input from data providers and R&D projects, and of course updates from all the projects providing the core portfolio of CAMS. Thank you for giving such honest presentations on status, recent highlights, and also the challenges and proposed solutions and the way forward, next steps. This facilitates a fruitful discussion and further development of the service. So I say this every year, but it's so good to meet in person. I think this is really important when we do this once a year, and to connect with all the different levels and parts of CAMS and associated partners. These informal discussions are really invaluable. We get so much input, it's like a vitamin boost for the next year. And the whole service is kind of coming together here, demonstrating the big picture of CAMS, and also the strategy going forward becomes more apparent during the General Assembly. So here I would like to recall the speeches from yesterday's introduction session. I think the message was well conveyed, that CAMS products, tools, and information are used in the EU directives and regulations, and that CAMS provides invaluable information to the political domain and makes an impact on decision-making level. Please take this as a take-home message. Turning the page. CAMS is also evolving to enable even stronger decision-making tools at local, global, and policy or political level. with continuous development and improvement of the core portfolio, stronger connections to the member states through the National Collaboration Program, involvement of new user segments through the thematic hubs, and of course, the ramp-up and operationalization of the GHG monitoring services, to name some examples. Last year, we marked being halfway through Copernicus 2. And this year, we are already planning Copernicus 3 and the next multi-financial framework. And there's a lot to build on. Among the external factors, there are a lot of unknowns, such as the direction of the new commission after recent elections, and the general geopolitical situation, but Copernicus and CAMS are not any less relevant, more if anything. So please keep up your good imperative work and see you next year. Thank you.
Okay, so thank you. Thank you very much, Maria, for your nice words and your support. You are our policy officer, and that's nice to have you with us. So, end of the General Assembly, and we would like first to thank you so much. Thank you for those nice days, for the excellent presentations that we had. I think that it was great to have this overview, to share those thoughts about the current status of CAMS, of the services, but also the future. We have started to think about the next steps and what we will be able to deliver. We have heard yesterday that we will have to deal with some objectives and challenges, very exciting, but okay, also very demanding. So, but I'm sure that we will be ready. This is a really nice community, and it was yes, for my first General Assembly as in that position, it was really great. So really, many thanks to all of you, many thanks to all the speakers and the CAMS teams. Also, many thanks to Belspo, who we co-coordinated the organization of this event. Many thanks to GoPA for the support. Richard, I think that we also would like to say thank you to Francesca, I think, because Francesca is the one. Please come on, Francesca. No, come on. I think that you have all been in touch with Francesca, because Francesca helped us to organize this event for many weeks, many months, and thank you so much for Francesca. Without you, it could have not happened. So many thanks, many thanks. Okay. Thank you. Many thanks to all of you. No, not much to say. Richard, would you like to say something? Thank you. Goodbye.
Now I can say a few words. First, I've really enjoyed this week. I hope it was the same for you. I think it was a really nice combination of informal interactions, some more formal interactions. We had scientific discussions. We had discussions with users, getting feedback, getting really positive feedback from the Commission, looking forward with the research projects. And I really want to thank Lucas as well for being here and moderating this session, and thanking our very, our future CAMS management, who knows. Yeah, really excellent presentations, and I told you we would keep the best for the end. So yeah, for me it was a perfect General Assembly, exactly the right mix. So I really hope it was the same for you. It was nice to be here. I arrived completely wet on Monday morning, but we have been able to turn it around. The sun is shining. I don't think we have decided where we'll meet next year. So we'll keep it a secret. But yeah, we thank Brussels and the organization here for being here. And we'll keep in touch. There's lots of work to do. There's lots of new opportunities. There will be a whole range of new ITTs, so look on our pages. We keep trying to improve how we interact with you based on your feedback. And we know you are equally working as hard as we are trying to do. So really looking forward to the coming year, and we'll meet again next year. Thank you very much.
So goodbye.